Okay, so this is, it's not going to be hard at all what I'm going to do, but it's going to be slightly technical. Okay, it's going to be slightly more, more calculations than what I did so far. Okay, less conceptual in a sense. So here I'm going to record everything that I need about duality. So I will just remind you all the basics. It's going to be not too difficult. So let me just remind you that if you have a convex function phi, the Fenchel dual phi star of theta. So I'm going to write theta for dual variables. This is just the maximum over all x in Rn of the inner product x dot theta minus phi of x. Okay, so you can, there are many, many ways to see this. This is just a bunch. I'm taking the maximum of a bunch of linear functions with a certain offset which matches the phi function. Okay, so this is a definition of a Fenchel dual. Good. So remember, what are we looking at? So the mirror descent flow is the following thing. X dot of t is equal to minus the Hessian of phi at xt inverse applied to some eta times gt plus lambda t, where lambda t is an element of the normal cone of k at xt, and xt is in the convex set k. Okay, so what I'm going to do in this lecture, what I want to do right now for this hour, is to discretize this algorithm and do the discrete time analysis. Okay, so you remember the various miracles. So the first miracle was just some robustness. The second miracle was the following calculation. So what I'm going to do to discretize for the moment, I'm going to ignore this. Okay, so I'm going to ignore the Lagrange multiplier for the moment. I'm just going to assume that I run without any constraint. Okay. So what was the second miracle? The second miracle was this calculation, the time derivative of the Bregman divergence between any fixed point y and x of t. If I don't have the Lagrange multiplier, it's actually equal to eta gt inner product with y minus xt. And you remember the rationale was that if I pay more, if gt.xt is much bigger than gt.y, then I regret for not being at y, and so this thing becomes very negative, so I learn. Okay, I get closer to y in Bregman divergence. The third miracle that we saw yesterday was that the derivative of d phi between y of t and x. We said that this was bounded by a Lipschitz constant times the norm of y dot of t. Okay, and we said that this you can use to track the optimum. Okay, so this was the tracking miracle. This is a potential miracle. This is a tracking miracle. What we're going to do now, because we want to do a continuous time analysis, discrete time analysis. Okay, so this was all continuous time. In the discrete time analysis, we will have a second order term. Okay, all of these equations will be true plus a little something. Okay, what is the little something? The little something is a second order derivative. Okay, so I'm going to look at the second order derivative. It's going to be some function of eta squared. Okay, so this function of eta squared, this term that is a multiple of eta squared, that's going to be the second order term. And this second order term is going to be extremely special and exactly adapted to what's called bandit feedback. Okay, and again, this is a miracle because it was absolutely not developed for this reason, but it just falls out. So let's do it. So from now on, we're going to, at least for today, we're going to mostly talk about regret analysis. So we're going to fix a certain y. So we're not going to care about miracle number 3. We only care about miracle number 2. Okay, so I only need to look at the second derivative of d phi between y and x of t. Okay, and that's why I ignored the Lagrange multiplier for the moment because, again, now it's an equality, so I can literally differentiate this thing. And let's say we are at time step where g of t is constant. Okay, so assume g of t is locally constant. And this is perfectly justified in the type of application that we have in mind because there is some cost function that you receive and you can basically present it, the same value for a long time, for a certain continuous time. So let's assume that g of t is locally constant in time, and let's see what is the time derivative of this. Well, we just have the time derivative of that, so it's exactly minus eta g of t inner product with x dot of t. And what is x dot of t? It's, minus the inversion of eta gt. So what do we find? We find that this is eta gt inner product with the inverse Hessian of phi at xt applied to eta gt. Which in notation in terms of the local norms that I mentioned before, you remember this local norm, the local norm of h at x, let's say squared, is just h inner product with the Hessian of phi at x, h. And the dual norm of this, let's say if I have a g, the dual norm of this norm is just with the inverse Hessian. Okay, so these are just notation. I have a local norm at the point x, which is given by the Hessian, and I have a dual norm, which is given by the inverse Hessian. Now, I recognize what is this thing. This thing is exactly eta squared times the local norm of gt at xt dual squared. Okay, and this is the miracle. This thing is going to be exactly what we need for bandit analysis. But first, before we do the bandit analysis, let's see how to use this to do a discrete time analysis of mirror descent. And maybe first let's define exactly what is discrete time mirror descent. This is not clear yet. Okay, so discrete time mirror descent. So again, I explained to you before, right? If I want to integrate this first line over time, so what do I have? I have the Hessian phi applied to x dot, which is the same thing as the time derivative of the gradient of phi. Okay, so continuous time mirror descent without constraint is exactly d over dt of grad phi of xt is equal to minus eta gt. So doing a discretization of this is very clear. Continuous discrete time mirror descent would be just grad phi of xt plus 1 minus grad phi of xt is equal to minus eta gt. Okay, so that's the definition of mirror descent when you don't have constraints in discrete time. But what about constraints? So with constraints, what happens is you can do this update, but you might fall outside of the set of constraints. So then you need to project back on the set of constraints. And of course, you're not going to do a Euclidean projection. I mean, the Euclidean norm doesn't have any special meaning in all of what we're doing. So what you're going to do is that you're going to project according to the Bregman divergence. This will be exactly the right thing that makes everything work, and we're going to see why. So with constraint, let zt plus 1 be such that grad phi of zt plus 1 is equal to grad phi of xt minus eta gt. Okay, so that's your first update. Again, this might be a non-feasible point. Now, what is going to be xt plus 1? Xt plus 1 is going to be the projection, the argmin over x in k of the Bregman divergence between x and zt plus 1. Okay, it's going to be the closest point in k to zt plus 1 according to this notion of distance, which is the Bregman divergence. This is the mirror descent algorithm, as it was written in discrete time by Nemirovsky at the end of the 70s. Okay, any question on this? So the theorem that we're going to prove, and I think it will take probably the rest of this hour. So the theorem is going to be like this. Maybe what do we let me just think if I want to give you some intuition. What do we expect So okay, maybe before I write the theorem, what we expect for the regret. For the regret, what is the regret? The regret is the sum over T of the inner product gt dot xt minus y. Right? That's the regret. That's how much, when I take the inner product of xt with gt, that's how much I paid. If gt was a certain loss function and xt was a probability distribution, this is exactly my expected loss. But more generally, you can also think if gt was the gradient of a convex function, then this is an upper bound on the gap between the value of the function at xt and y. Anyway, this is what we care about, and we will see it again in concrete examples. So what do we expect? From miracle 2, we expect that this should be related to the drop in Bregman divergence. Okay, so from M2, this should be smaller than something like the sum over T of, what do we have? The Bregman divergence. So let's see, you have to put it on the other side. So you get the Bregman divergence between y and xt minus the Bregman divergence between y and xt plus 1. Okay, let's say with a 1 over eta. Right, this is a term which corresponds to the time derivative of d phi y xt. Okay, so maybe let's remove the sum just to clarify. So this term gt dot xt minus y, if we take inspiration from M2, which was a continuous time version, it should be related to this drop in Bregman divergence. Maybe let's put the eta here. But now we know it's not going to be exactly this because we have discretized the process. So there will be another term. What should be this other term? Well, from M4, we expect that the other term should be like eta squared, the dual local norm of gt. So from M4, we expect a plus eta squared, the dual local norm of gt at xt dual squared. Okay, this is what we expect. What we are actually going to prove is almost exactly that, except that instead of the dual local norm at xt, we're going to have some term which is some interpolation. So you need to understand what is this dual norm and how does it relate to the Bregman divergence. So let me write the theorem and then I explain. So the theorem, so this is actually true. The theorem goes like this. The sum for t equals 1 to capital T of the inner product gt dot xt minus y. This is upper bounded by, so I will have this term, which is a telescopic sum. So I get the Bregman divergence between y and xt, x1 divided by eta. And I get this second order term, which was eta squared, but I divide by eta. So I get, okay, but anyway, it's going to be 1 over eta, the sum for t equals 1 to capital T. And what I have here is this funny term, the Bregman divergence of the Fenchel dual between grad phi of xt minus eta gt and grad phi of xt. Okay, so instead of this very nice dual local norm, I get this Bregman divergence of the Fenchel dual. But I claim that these two things are very similar. So let me go back to my duality. Okay, so so first of all, is the statement of the theorem clear? Okay, so I get two terms. I get, again, think about the very first lecture when we analyzed gradient descent. There were two terms. There was a range term, the size of the set over which you're optimizing, and there was a variance term, which was the sum of the Euclidean norm squared of the gradient. So now all we have done is that we have a range which is not just the radius in Euclidean norm of the set, but it's a Bregman radius. And the variance term, instead of being those Euclidean norms, they are those local dual norms. Okay? And here, instead of local dual norms, we have this Bregman divergence. So why is this very close to the local dual norm? It's very close because of the following. So the Bregman divergence between x and y, this is roughly like x minus y, inner product with the Hessian of phi maybe at x, or yeah, at x, or maybe at let's say at y, applied to x minus y, right? With a 1/2. Doesn't matter the 1/2. Right? This is just Taylor's theorem. So the Bregman divergence of the Fenchel dual, what is it? Between, say, so here is a result. This thing, the Bregman divergence of the Fenchel dual between two dual points, this is actually equal to the Bregman divergence in the primal between x and y. Okay, so this is, I will leave it as an exercise. This is an exercise. It's an equality, so it's not too hard. And just how can you hope to prove this? Okay, what you have to understand is you have to understand what is phi star and what is the gradient of phi star. Okay, but it's very easy to analyze both what is phi star and the gradient of phi star. So let me just give you the basics of this. So denote x star of theta, maybe x of theta, for the maximizer. In phi star. So what do we have? We have that the gradient of phi star at theta, this is actually equal to x of theta. Right? Just think about it. Imagine that if this was a finite set, I'm taking the maximum of linear functions over a finite set. Then the gradient at any point is just, which linear function is it that I have right now? I have a slope, and what is the slope if I have the linear function x? The slope is x. Okay, so it's just the slope of the linear function at the maximizer, which is x. So the gradient of phi star of theta is x theta. But we also know, and what do we have? By local optimality at the optimum, what do we know? We know that the derivative of this thing with respect to x should be 0. What is the derivative with respect to x? It's theta minus grad phi of x theta. This should be 0. Okay, so those two identity, what does it give me? It gives me that grad phi of grad phi star of theta is equal to theta. Okay, so what I just proved for you is that the gradient of the Fenchel dual is the inverse of the gradient of the primal. Okay, so grad phi star is the inverse function compared to grad phi. When you compose them, you get the identity. But now I can also differentiate this thing. If I differentiate this thing, what do I get? I'm going to get the Hessian of phi star of theta multiplied by the Hessian of phi at grad phi star. Okay, so I also get that the Hessian of phi, let's see, maybe there is not enough space. Okay, so let me just do this last implication. So the last implication is that when I differentiate this thing with respect to theta, I'm going to get a term which comes from the inside, right? I just apply the chain rule. I get the Hessian phi star of theta applied to the Hessian of phi at grad phi star of theta. This should be the derivative, the Jacobian of theta, which is just the identity. Okay, what does it mean? This is a matrix, this is another matrix, and when you multiply them, you get the identity. Okay, so this is called an inverse. This says that the Hessian of phi star is the inverse of the Hessian of phi, with, of course, the right type check for the variables that you put in. So if you put in theta for phi star, you should put grad phi star for theta. for x here. Okay, so again, the gradient, they are all inverse of each other. The gradient of the differential dual is the inverse function of the gradient, and the Hessian of the differential dual is the inverse of the Hessian of phi. So that's why this term that I wrote here, which is a Bregman divergence of phi star, you should really interpret it as, it's a norm which corresponds to the Hessian of phi star, and the Hessian of phi star is the inverse Hessian of phi, which is nothing but this norm. Okay. So that term is basically the same as this one, up to a third order term. Okay, so there is here there was a second order term, but of course there is a third order term. I mean, there are all the terms. So what's very nice with this theorem is that we don't need to talk about the third order, the fourth order, all of that. They are all captured by the Bregman divergence. The Bregman divergence is exactly the right thing that makes everything work. Okay, so now I need to prove for you this theorem. That's what I'm going to do now. Are we good on that? And then in application, it's nicer to work with those things, so I will make some assumption. I will tell you what I need about the third order derivative of phi, so that this Bregman divergence is actually the same thing as that. Okay. Yeah. All right, so this was not the technical part, just to clarify. Technical part is a proof. So let's do the proof. Okay, I want to bound this thing. Okay, let's take it, term by term, and I want to be guided by what is written here, the continuous time thing. So let's take it term by term. So GT inner product with xt minus y. Okay, what is this? What do I know about those terms? I want to make GT disappear to make some, because GT disappear in the first order term. So I want to try to make GT disappear. What is GT? By definition, let's put a eta so that we don't have to carry this eta all the way. So eta GT, that's what? That's grad phi of xt minus grad phi of zt plus 1. Inner product with xt minus y. Yes, that's right. By definition of zt plus 1 is the unprojected point. It's when I do one step of mirror descent on eta gt. Okay, so grad phi zt plus 1 is grad phi xt minus eta gt. Okay, so here I really did nothing. What do I want to compare this to? I would like to compare this to this thing, the dropping Bregman divergence. Okay, what is this drop in Bregman divergence? Maybe I write it over here. Okay, so this is the real, below the red line is the real proof, and above the red line is calculation to guide us. Okay. So what is this box? So let's call it box. So box is the following. So what is box? It's, okay, so remember the Bregman divergence between y and x is phi of y minus phi of x minus grad phi of x inner product with y minus x. So you see the phi of y's I cancel. I get phi of xt plus 1 minus phi of xt. What do I get for the first order term? I get minus grad phi of xt inner product with y minus xt. By the way, please be awake and check everything that I do, because I'm going to make sign error and then I'm going to be confused somewhere. So I will need you to save me at some point. Okay, so minus grad phi of xt, and here I have a minus minus, so plus grad phi of xt plus 1 inner product with y minus xt plus 1. Okay, so this is the drop. Maybe box was not a good term. Drop. This is a drop, right? The drop in Bregman divergence. The improvement in the potential. Okay, so I would like to make appear drop. Okay, so I'm pretty far to having drop here. What do I have? I have this term. Right? I have this term, grad phi of xt inner product with xt minus y. Okay, so I'm happy about that. And it's with the right sign, right? There is a minus here, and here it's opposite. So that's good. Then I have grad phi of zt plus 1, whereas I would like to have grad phi of xt plus 1. Okay? So that's a problem I will need to fix. And also, instead of having xt minus y, I mean xt plus 1 minus 1, I have y minus xt plus 1. So let's try to make terms appear one by one. So the first term I'm going to try to make appear is to have an xt plus 1 here. Okay, so again, what am I saying? I'm just saying there is grad phi of xt inner product with xt minus 1. This term I keep, I'm happy with it. Now I have minus grad phi of zt plus 1. This term I'm not happy for two reasons, because it's zt plus 1 and not xt plus 1, but also because it's xt minus y instead of being y minus xt plus 1. So let's make appear xt plus 1 first. So what do I get? I get xt minus xt plus 1. That's a term I will have to deal with somehow. And then I get minus grad phi of zt plus 1 inner product with what? With xt plus 1 minus y. Okay. So now I need to somehow deal with this term, remove it altogether, and here I need to replace zt plus 1 by xt plus 1. What do I know about the relation between zt plus 1 and xt plus 1? I only know one thing, which is that xt plus 1 is a projection of zt plus 1. So let's look at the first order optimality condition for this definition. Where do I do that? Yeah. Let's do it here. I mean, okay, just what am I trying to do? This proof has been written like hundreds of times in the literature, but it has always been called the magical proof. What I'm trying to show to you is that there is nothing magical about it, and you can come up with it from first principle just by tracking all the terms and being guided by the continuous time analysis. If I could also just, do the calculation and show that you get the right answer, but this is less insightful. That's what I'm trying to do, just to. Okay. So what do we know? So again, we want to replace zt plus 1 by xt plus 1. And what do we know? xt plus 1 is the argmin over x in k of grad phi of Bregman divergence between x and zt plus 1. Okay, so this is constrained convex optimization. So what do I know? At the optimum, the gradient is positively correlated with any direction going inside. So I know that the gradient with respect to x of d phi at xt plus 1, zt plus 1, this object is positively correlated with any direction going inside, which is y minus xt plus 1. This is non-negative for any y. Right? This was like lemma 1 of all those lectures. At opt, the gradient is positively correlated with any direction going inside. What is the gradient with respect to x of the Bregman divergence? I have a phi of x, which gives me a grad phi of x. And then I have a minus grad phi of y inner product with x, which gives me a grad phi of y. So this is grad phi of xt plus 1 minus grad phi of zt plus 1. Okay, the gradient of this Bregman divergence is exactly the difference between the gradients. So grad phi of xt plus 1 minus grad phi of zt plus 1 in a product with y minus xt plus 1 is non-negative for any y, which I hope is exactly what I wanted. So let's see. So eventually I want to upper bound this thing. So there is a minus sign. Let's see if we can lower bound it. Okay, it's just, yeah. So let's take the minus sign together. So we want to upper bound this thing. So with the minus, it's y minus xt plus 1. And it's exactly what we want. If I put this grad phi on the other side, I get grad phi zt plus 1 in a product with y minus xt plus 1 is upper bounded by grad phi xt plus 1 in a product with y minus xt plus 1. Okay, so this is upper bounded by grad phi of xt plus 1 in a product with xt plus 1 minus y. Okay, we're getting there, right? We got one more term, which is this one. Okay, so now let's write what we have. We have that this is upper bounded by the drop, except that in the drop we have this term, so we need to do plus phi of xt plus 1 minus phi of xt plus 1. Sorry, plus phi of xt minus phi of xt plus 1. And we have this term, which we haven't accounted for yet, minus grad phi of zt plus 1 in a product with xt minus xt plus 1. Okay, but this is starting to look fairly reasonable. This smells like a Bregman divergence type term again, except that, you know, it would be a Bregman divergence term if it was phi of zt plus 1 here. I mean, it would be Bregman divergence if a couple of things were different. So let's let me see, what am I saying here? Right, okay. Yeah, so we're almost there. We're very, very close right now. So let me see. Okay, maybe I don't try to motivate this term. This is part of the theorem. That's what we want to prove. Maybe I don't motivate it. Let's just see. Let's just rewrite it. We don't have Fenchel duals here, so let's go back to the primal. Okay, so again, these are just like kind of intuitions part. So the Bregman divergence between phi star of grad phi xt minus eta gt. Oh, we have a name for this. This is grad phi of zt plus 1. Oh, yeah, okay, we're there. Okay. So this, right, we are allowed to have a remainder term. Right, again, we want to say this is bounded by the drop plus something which looks like this thing. And this thing is exactly that. Sorry, that's the definition, right? Grad phi xt minus eta gt. That's the definition of zt plus 1. So this is what we have. And now I'm just going to use this formula that I didn't prove for you. But it's a super simple exercise given those formulas. So what is this? This is d phi between xt and zt plus 1. Right? So the remainder term that I want to make appear is d phi of xt zt plus 1, which is phi of xt minus phi of zt plus 1 minus grad phi of zt plus 1 inner product with phi of x inner product with xt minus zt plus 1. Yes. Okay, so let's make appear this term here. Okay, that's all I want to do right now. So what do we have? I mean, this thing is equal, or maybe in white, this is equal, this part, without the drop, or maybe, okay. With the drop, it's equal to drop plus this term, d phi xt to zt plus 1. Now what do we have which is not correct? We have the phi of xt. Now we are missing the phi of zt plus 1, so let's add the phi of zt plus 1. We are missing this minus phi of xt plus 1. And what do we have for this term? We have grad phi of zt plus 1 dot xt. We have it here. But instead of zt plus 1, we have xt plus 1 here. So what we have is minus grad phi of zt plus 1 inner product with zt plus 1 minus xt plus 1. And now we're very happy. By convexity, this term is non-negative. This thing is simply non-negative. Non-positive, sorry. Right? By convexity, phi of zt plus 1 minus phi of xt plus 1 is smaller than grad phi of zt plus 1 inner product with zt plus 1 minus xt plus 1. So we exactly have that this is non-positive. So that's it. That's the proof. Okay, that's the complete proof. Like the complete proof of this theorem are just those 3 lines. But if you don't know what are the right object to make appear, it can get pretty confusing. Okay, is there any question on this before I use it? I mean, there was nothing really so exciting. It's not conceptual here. These are just calculations. The conceptual parts are all these miracles. This is just working it out. But it's going to be extremely useful. For instance, what I'm going to do for you right now is to redo the multiplicative weights analysis, but without being smart. I mean, because I just, you have the philosophical part, the conceptual part, then you just do the technical details, and you apply it to the entropy, and the result falls out. Whereas if you remember the multiplicative weight update, it needed some genius to come up with it. Okay, so it's completely, yeah, okay. All right, so let's do an application of this, and then after the break we will do the information geometry part. So right now we're not going to do the information geometry. I'm just going to recover multiplicative weights update. So revisiting multiplicative weights update. Okay, so you remember you have a loss, LT, which is, let's say, in 0, 1 to the n. And what we're going to do is that we're going to run discrete time mirror descent with the entropy. And again, the motivation for the entropy, for instance, you can take it from the derivation that I did for metrical task system. It's the exact same argument. But right now, let's just say we have the good idea to say, let's change the geometry of gradient descent by replacing the Euclidean norm by the entropy. Right, maybe I didn't say it yet, but gradient descent is nothing but mirror descent with the mirror map phi being the Euclidean norm squared. Okay, so we're just replacing the Euclidean norm squared by something else, which is more L1-ish. Okay, so first let's derive what is the algorithm. And let me put a minus xi. Any linear term doesn't matter, but just to simplify what I write. So grad phi of x, this is a vector with entry log of xi. So when I do the update, grad phi of zt plus 1 is equal to grad phi of xt minus eta lt. This is actually equivalent to saying that the log of zt plus 1 at any coordinate is equal to the log of xt as that coordinate minus eta lt as that coordinate. So when I take the exponential, what do I get? I get zt plus 1 of I is equal to xt of I e to the minus eta lt of I. So you see, if my losses were either 0 or 1, what happens is that the coordinate, either I don't update them, or if they got a loss, I downweight their value by e to the minus eta, which is like 1 minus eta. Next, I need to tell you, okay, so this is kind of an update at the weight level. I downweight, certain coordinate. But now I need to tell you how do I get a probability distribution. How do I get a probability distribution? I project this with the Bregman divergence. Now I'm going to show to you very simply that projection with the Bregman divergence of the entropy on the simplex is just normalization. So xt plus 1 is in fact just going to be zt plus 1 normalized by the L1 norm of zt plus 1. So this is exactly the multiplicative weight update. Okay, so again, now we have xt plus 1 is equal to the argmin of d phi of x zt plus 1 over x in the simplex. And you remember we already did this calculation. Let me think. Yeah, let's just do it like this. So what do I know? I know again that the gradient of this thing is positively, it's in the normal cone. Okay, so this is equivalent to saying that grad phi of xt plus 1 minus grad phi of zt plus 1 is in fact equal to a term lambda t, which is in minus the normal cone, or maybe minus lambda t, where lambda t is in the normal cone at zt plus 1, at xt plus 1. But you remember, we know exactly what is the normal cone of the simplex. There are Lagrange multipliers that corresponds to the non-negativity constraint, but I don't care about them because the entropy blows up at 0. So it's never going to turn something to 0. So there is only one term in the Lagrange multiplier, which is the one corresponding to the sum should be equal to 1. So this Lagrange multiplier, it's really equal to some mu t times the all one vector. Okay, so what does that mean? That means that in terms of log, I get log xt plus 1 of I is equal to log minus, or is equal to log zt plus 1 of I plus log mu t. Okay, so multiplicatively, xt plus 1 is just zt plus 1 plus a constant, which means, like, for real, xt plus 1 is zt plus 1 times a constant. Okay, so xt plus 1 is proportional to zt plus 1, okay, which is equivalent to xt plus 1 is proportional to zt plus 1. Okay, that's the same thing when you say that you have an added constant in terms of the log. It just means that the two vectors are proportional to each other. So xt plus 1 is a vector whose entries sum up to 1, which is proportional to zt plus 1. So this is just zt plus 1 divided by the L1 norm of zt plus 1. Okay, that's the only solution. So you find that mirror descent with the entropy on the simplex, just by using those general formula, gives you back the multiplicative weight update algorithm directly. Yeah.
So the more conceptual question then is why we associate the entropy with the simplex. I mean, of course, we say, oh, it's a Cox function, the simplex or whatever, but...
Yeah, so I think we gave a pretty good answer yesterday when we did the metrical task system. And we realized that if you wanted to match the movement cost with the service cost, then you have a certain, and you remember I did this thing where you write phi of x is just a sum of, let's say, phi of xi. You just look for a separable function, and then we found this identity that we wanted to have 1 over phi double prime of s is equal to s. That came from the intuition that we said we want the movement cost to be proportional to the service cost because the service cost just, works directly automatically for mirror descent. So the entropy came out very naturally. And I also said that metrical task systems are strictly more general than prediction with expert advice. So while I agree that here it's not necessarily clear why you would use the entropy, I think if you look at the canonical problem, which is metrical task system, you naturally are led to this. Yeah, that's my explanation. What people say in general, but I don't like it, is they say that the entropy is strongly convex with respect to the L1 norm, which is Pinsker's inequality, which is true. But yeah, you need to know Pinsker's inequality. I mean, it's not that simple anymore. I mean, it's also fine. It's also a fine explanation. But I prefer that one. Yeah.
Just out of curiosity, if you look at something that's entropy-like, these Renyi entrophies and things like that, this kind of calculation would give you some C-formed way of normalizing. Do you know what those things?
Yeah, of course. Yes, we're going to see that. I mean, we're going to talk about it. Yeah, yes. Yes, there are other forms of entropy, and they might be useful for other things. Yeah, we're going to talk about that. Okay, maybe I don't want to rush it. What I'm going to do after the break, very simply, is now I have multiplicative weights, and I can analyze it with this very general theorem. So I'm just going to work out what is this term in this case, and you will see that the analysis that we did just falls out completely immediately. And then we will move on to bandits, which are very interesting for a variety of reasons, but in particular, in bandits, it will be very important to have those local norms. Okay, so that will be for after the break. Thanks.